ನಮಸ್ತೆ ಡಿಯರ್ ಸ್ಟೂಡೆಂಟ್ಸ್, ಪ್ರೀತಿಯ ವಿದ್ಯಾರ್ಥಿಗಳೇ. PU ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಬೆಂಗಳೂರು, ಜಿಲ್ಲಾ ಪಂಚಾಯತ್ ಉಡುಪಿ ಸಹಯೋಗದೊಂದಿಗೆ ಸರ್ಕಾರಿ ಪದವಿ ಪೂರ್ವ ಕಾಲೇಜಿನ ವಿಜ್ಞಾನ ವಿಭಾಗದ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ KSET ನೀಟ್ ಟ್ರೈನಿಂಗನ್ನು ಕೊಡ್ತಾ ಇದ್ದಾರೆ. ಈ ಟ್ರೈನಿಂಗಿನ ಭಾಗವಾಗಿ ನನಗೆ ಸೆಕೆಂಡ್ PUC ಫಿಸಿಕ್ಸಿನ ಒಂದು ಚಾಪ್ಟರ್ನ ಅಸೈನ್ ಮಾಡಿದ್ದಾರೆ. ದ ಟಾಪಿಕ್ ಗಿವನ್ ಫಾರ್ ಮೀ ಈಸ್ Semiconductor Electronics. Second PUC Physics last chapter number 14. Myself, CHAMARAJ lecturer in physics, GPUC with Calcutta. To start with, what and all the concept you studied in this chapter, just have a glance about that chapter. To start with, synopsis. The important points to be covered in this chapter are: see, the meaning of energy band. What do you mean by energy band? The energy band meaning of energy band. What is energy band? The range of energy available for an electron in an atom is called energy level. But if you consider a solid, a piece of solid contains billion number of atoms. These energy levels are converted into energy bands, or the range of energies available for electron of an atom in a solid. That range of energy is called energy band. Here in energy band we have valence band and conduction band. What do you mean by valence band? The energy band which includes energy levels of the valence electron. Energy levels, valence electron ಗಳ energy levels ಅನ್ನು ಹೇಳ್ತೇವೆ. In a solid we say valence band. The energy band which is above the valence band is called conduction band. There is a small energy gap between conduction band and valence band. That energy gap is called forbidden gap or energy gap. On the basis of energy band, these solids are classified into three types. We know metals which have overlapping conduction and valence band. Conduction band, valence band, both are overlapped. Now move on to insulator. The insulators are the one in which there is a large energy gap between valence band and conduction band. Conduction band is empty, valence band is filled. There is a large energy gap. Energy gap is greater than 3 eV. Then the intermediate stage between conductor and insulator is called semiconductor. This is a very important topic for us. Semiconductor. In the case of semiconductor, energy gap is less than 3 eV. In a pure semiconductor, we have only two elemental semiconductors, silicon and germanium. Pure semiconductors are also called as intrinsic semiconductors. Intrinsic means pure. In the intrinsic semiconductor, the number of free electrons is equal to number of holes. That is equal to intrinsic carrier concentration. Ne is equal to Ni is equal to Nh. The drawback of this intrinsic semiconductor is electrical conductivity is low. Move on to the next slide. Extrinsic semiconductor. What do you mean by extrinsic? Extrinsic semiconductor is also called impure semiconductor. Impure. impure. When we add dopants or impurity atoms to the pure semiconductor, it becomes impure semiconductor or doped semiconductor, or it is also called extrinsic semiconductor. In case of extrinsic semiconductor, there are two types depending on the number of holes or number of free electrons which are more in number. There are two types. So Ne is not equal to Nh, where Ne is electron concentration, Nh is hole concentration. See, they follow a relation Ne into Nh is equal to Ni square. Ne is into Nh is equal to Ni square. Keep in mind, in extrinsic semiconductor, number of dopant atoms, for example, in case of N-type semiconductor, dopants are pentavalent, they are called donor atoms. Nd is equal to Ne, number of free electrons. And in case of P-type semiconductor, dopants are trivalent in nature, so they are called acceptor impurity atoms. Na is also equal to Nh, number of holes. That means each impurity atom added to the semiconductor generates extra free electron or extra hole in the semiconductor. See, the process of adding impurity to the pure semiconductor, pure semiconductor is called doping, and impurity atom is called dopant. The condition for doping are sizes of the dopant and semiconductor atom should be nearly same. Size of impurity atom and size of semiconductor atom should match. Dopant should not alter the original semiconductor crystal structure. The addition of dopant should not change the crystal structure of semiconductor. Types of dopant for silicon or germanium to convert it into N-type and P-type semiconductor are pentavalent impurity atoms are arsenic, antimony, phosphorus. Trivalent impurity atoms are indium, boron, aluminium. Move on to the next slide. Semiconductor diode. See, if we prepare N-type and P-type semiconductor separately, and if we keep the semiconductors separately, then it is of no use. To make it practically useful, what we have to do is this. We have to join N-type semiconductor with the P-type semiconductor with a special technique called fabrication technique or integrated technology. It is possible to construct a PN junction. It is also called a semiconductor diode. This is the symbol of semiconductor diode, where triangle is P side, line is N side. As soon as the junction is formed, we know there are three processes taking place: diffusion of majority carriers due to concentration gradient, and formation of depletion layer. Then, due to the formation of depletion layer, a small amount of potential difference exists across the junction. That potential difference is called barrier potential. Due to this barrier potential, there exists an electric field across the junction from N side to P side, and this electric field starts drifting the minority carriers. The last process is called drifting. Drifting takes place for minority carriers. diffusion takes place for majority carriers. In semiconductor diode, when we apply external voltage, the process of applying external voltage to the semiconductor diode is called biasing. There are two types of biasing, forward bias and reverse bias. In forward bias, P side is connected to positive terminal, N side is connected to negative terminal. The property of forward bias is current maximum, resistance minimum, width of the depletion layer decreases, barrier potential decreases. The second type is called reverse bias. When P side is connected to negative, N side is connected to positive, the diode is said to be in reverse bias. So, during reverse bias, current due to majority carrier 0. A small amount of current exists due to the drifting of minority carriers is called reverse saturation current, which is very, very small. The resistance, width of the depletion layer increases, depletion layer width increases, and resistance is maximum. Resistance is maximum. Then the main use of PN junction is rectification. The main use of PN junction is rectification. What is rectification? The conversion of AC into DC. Alternating current is converted into direct current by the use of semiconductor diode. The constructed circuit is called rectifier. There are two types of rectifier. One is called half wave rectifier, which converts only half of the input signal voltage into pulsating DC voltage. Why it is called pulsating DC voltage? Because the pure DC waveform is like this. If you see the output voltage of half wave rectifier, just you see it is not pure DC. AC component or ripple is present in the output. So it is called pulsating DC. So rectifier converts AC into pulsating DC, not pure DC. Here only one half cycle of AC is converted into DC. Here we make use of only one diode, general step down transformer and a load resistance. During positive half cycle of input signal, secondary upper terminal is positive, lower terminal is negative. So the diode is in forward bias. Current flows through the diode producing output voltage. So I write here on, diode is on. Similarly, during negative half cycle of the input signal, what happens is upper end of the secondary becomes minus, lower end becomes plus. So the diode is in reverse bias. Current due to majority carrier is 0, output is 0. No output here. D off. Diode is off. Similarly, the same process repeats. So for one complete cycle of input signal, we have only half cycle of output. Half cycle of output, or only positive half cycles are converted into pulsating DC. Negative half cycles are missing. Suppose if you connect the diode in reverse order, for example like this, ಈ ಡಯೋಡನ್ನು ಹೀಗೆ ನೀವು ಕನೆಕ್ಟ್ ಮಾಡಿದರೆ ಆಗ the output will be like this. Positive half is missing, negative half we get pulsating output, positive half is missing, negative half we get output. So in both the cases we get only one half of AC is converted into DC. We move on to the next full wave rectifier. It is an electronic circuit. containing two diodes and a special type of transformer called a center tap transformer. Center tap transformer. It is a specially designed transformer such that the secondary of the transformer has three terminals. Secondary has three terminals with the central terminal is connected to ground. Illi nodi, center terminal of the secondary connected to ground. And the circuit contains two diodes, D1 and D2. In half-wave rectifier, we used only one diode. Here we have two diodes and a special type of transformer called center tapped transformer. Center tapped transformer. So, during the positive half cycle of the input signal, as we know, upper end is positive, lower end is negative. The diode D1 is in forward bias, the lower diode is in reverse bias. So, current flows through the diode in this direction, like this. Here we write output due to D1. Output is produced due to the first diode. Now we move on to the second half of the input signal. Second half cycle of the input signal. During that, polarity changes. So, biasing condition of the diode also changes. That means upper diode becomes now reverse bias, lower diode forward bias, lower diode conducts, upper diode does not conduct or it is in off state. So, current is produced or output is produced across the load resistor due to D2. The same procedure continues. This is, so both half cycles of AC, both positive and negative half cycles of AC are converted into DC. This is about full wave rectifier. Now we move on to the special purpose diodes. The first diode we have Zener diode. It is a special purpose semiconductor diode designed to operate under reverse bias. Operation of Zener diode is in reverse bias. It is very important. This is the circuit symbol of Zener diode. Then the main use of Zener diode is to stabilize the voltage or voltage regulator. Voltage regulator. And the working you already studied in detail in class. Next we move on to photodiode. Photodiode is an optoelectronic device which operates in reverse bias used to detect the light signal. Photodiode is a special purpose PN junction diode which converts light energy into electrical energy. So, the detection of light signal is done by using photodiode. Next, solar cell. Solar cell is the one which is also PN junction which generates EMF when solar radiation falls on the PN junction. The generation of EMF by a solar cell takes place in three different processes. Generation of electron hole pairs. When light is falling in the depletion layer, holes and free electrons are generated. They are separated, then they are collected, thereby producing voltage. Next we move on to logic gates. Logic gates are the digital circuits which follow certain logical relationship between the input and output. We have 5 logic gates in our syllabus. The first one is called NOT gate, which gives complement of the input. That is, if input is A, output is A bar. If input is low, 0, output is 1. If input is 1, output is 0. The second gate is called OR gate. Here, OR gate is the one which produces output 0 when both inputs are 0. This is to remember for OR gate. 0, 0 is 0 or else it is 1. And the next gate is called AND gate. Here you should remember for AND gate, high input gives high output. Otherwise, the output is 0. 1, 1 is 1 for AND gate. 0, 0 is 0 for OR gate. NOT gate gives complement of the input. NAND gate. When AND gate is followed by NOT gate, the resulting gate is called NAND gate. AND gate ಗೆ ಒಂದು NOT gate ಅನ್ನು ಸೀರೀಸ್ ಆಗಿ ಕನೆಕ್ಟ್ ಮಾಡಿದರೆ we get NAND. So the output of NAND gate is A, B bar, because AB is the input of output of AND gate. Complement is the output of NOT gate. So AB bar is the output of NAND gate. This is the A. If both are 0, then 0, 0 is 0, AND gate, complement, so output is 1. 0, 1, AND gate output is 0, complement is 1. So for NAND gate, you should remember when both inputs are high, output is 0. Next, we move on to the last gate. It is called a NOR gate. NOR gate. When OR gate is connected with NOT gate, we get NOR gate. The equation of NOR gate is A plus B complement. A plus B complement. For NOR gate, you should remember 0, 0 is 1. Rest all the outputs are zeros. Because for OR gate, 0, 0, 0, but NOR means complement of OR, so it is 0, 0 is 1, rest all the outputs are zeros. These two gates, NAND gate and NOR gate, are called universal gates. NAND gate and NOR gates are called universal gates because by using these gates, it is possible to construct OR and NOT gates that we see in our questions. This is about the main points of this chapter. Now we move on to the mind map of this chapter. What and all it contains: energy bands, classification of solids, intrinsic semiconductor, extrinsic semiconductor, rectifier, full wave rectifier, half wave rectifier, forward and reverse bias of the diodes, then logic gates, light emitting diode, Zener diode, photodiode. This is the whole chapter consists of these concepts. With this introduction, we move on to the questions now. Just you see, read the question 2 or 3 times. A silicon specimen is made into a p-type semiconductor. A silicon specimen, silicon is a pure semiconductor, is made into a p-type semiconductor by doping on an average of 1 indium atom per 5 into 10 power 7 silicon atoms. 5 into 10 power 7 silicon atoms ಗೆ ಒಂದು ಇಂಡಿಯಂ ಆಟಮ್ ಅನ್ನು ಆಡ್ ಮಾಡ್ತಾರೆ. ಅರ್ಥ ಆಯ್ತಾ? If the number density of atoms in the silicon specimen is 5 into 10 power 28 atoms per centimeter cube. Per meter cube. 1 meter cube size ಇರುವ ಸಿಲಿಕಾನ್ ಅಲ್ಲಿ 5 into 10 power 28 atoms ಇದ್ದಾವೆ. Then the number of acceptor atoms or impurity atoms in silicon per cubic centimeter. Per cubic centimeter ಎಷ್ಟು acceptor atom ಅನ್ನು ಆಡ್ ಮಾಡಬೇಕು ಅಂತ ಕೇಳಿದ್ದಾರೆ. See here 5 into 10 power 7 silicon atoms ಗೆ ಒಂದು ಇಂಡಿಯಂ ಆಟಮ್ ಅನ್ನು ಆಡ್ ಮಾಡ್ತಾ ಇದ್ದೇವೆ. That is impurity ratio. 5 into 10 power pure 10 power 7 ಪ್ಯೂರ್ ಸಿಲಿಕಾನ್ ಆಟಮ್ಸ್ಗೆ ಒಂದು ಇಂಡಿಯಂ ಆಟಮ್ ಅನ್ನು ಆಡ್ ಮಾಡ್ತಾ ಇದ್ದೇವೆ. ಪ್ಯೂರ್ ಸಿಲಿಕಾನ್ ಅಲ್ಲಿ 1 ಮೀಟರ್ ಕ್ಯೂಬ್ ಆಫ್ ಪ್ಯೂರ್ ಸಿಲಿಕಾನ್ ಕಂಟೈನ್ಸ್ 5 into 10 power 28 ಆಟಮ್ಸ್. ಈಗ 1 ಸೆಂಟಿಮೀಟರ್ ಕ್ಯೂಬ್ ಅನ್ನ ಇಂಪ್ಯೂರ್ ಸೆಮಿಕಂಡಕ್ಟರ್ ಮಾಡಲಿಕ್ಕೆ ಎಷ್ಟು ಇಂಪ್ಯೂರಿಟಿ ಆಟಮ್ಸ್ ಅನ್ನು ಆಡ್ ಮಾಡಬೇಕು ಅಂತ. First, what we have to do is this. First, consider 1 meter cube ಅಲ್ಲಿ 5 into 10 power 28 atoms ಸಿಲಿಕಾನ್ ಆಟಮ್ಸ್ ಇದ್ದರೆ 1 ಸೆಂಟಿಮೀಟರ್ ಕ್ಯೂಬಲ್ಲಿ ಎಷ್ಟಿರ್ತದೆ ಅಂತ ನೋಡ್ಕೊಳ್ಳೋದು. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ 1 centimeter cube means how many meter cube? 10 power minus 6 meter cube. For this, multiply by 10 power minus 6. We get n is equal to 5 into 10 power 22 atoms per centimeter cube. So, to convert 1 centimeter cube silicon into p-type semiconductor, the number of impurity atoms added is for 5 into 10 power 7 atoms, we are adding 1 impurity atom. For 5 into 10 power 22 atoms, how many number of atoms required? Say that is capital N. If you simplify, we get 10 power 15 atoms per centimeter cube. That is, option C is the right answer. Just we see the solution. See, number density of atoms in silicon specimen 5 into 10 power 28 atoms per meter cube, convert into per centimeter cube 5 into 10 power 22. Since one atom of indium is doped in 5 into 10 power silicon atoms, so the number of indium atoms doped per centimeter cube of silicon is n is equal to 5 into 10 power 7 ಗೆ ಒಂದು ಆಟಮ್ ಹಾಕಿದರೆ 5 into 10 power 22 ಆಟಮಿಗೆ ಎಷ್ಟು ಹಾಕಬೇಕು ಅಂದರೆ 1 into 10 power 15 atom per centimeter cube. So the option is option C is the right answer. Now we move on to next question. See the question carefully. Serious drawback of semiconductor diode or semiconductor devices. Serious drawback of semiconductor devices. Just you read all the 4 points, which is the correct answer. We know semiconducting devices works only at low temperature, low voltages. Low voltages, or they are low power devices. Here they given serious, they cannot be used with high voltage. They pollute the environment. They are costly. They do not last for long time. Here, just you read the question carefully. The solution is the first one is the serious drawback. That is, they cannot be used with high voltage because they are low voltage devices. High voltage ಗೆ semiconductor devices ಅನ್ನು ಯೂಸ್ ಮಾಡಲಿಕ್ಕೆ ಆಗುವುದಿಲ್ಲ. That is the serious drawback. Now we move on to the next question. It is also theory based question. direct theory based question. Which of the following statements is not true? Yes, you see, ಈ 4 ಸ್ಟೇಟ್ಮೆಂಟ್ ಏನು ಕೊಟ್ಟಿದ್ದಾರೆ ಅದರಲ್ಲಿ ಸರಿ ಅಲ್ಲದ್ದು ಯಾವುದು ಆರ್ ಫಾಲ್ಸ್ ಯಾವುದು ಅಂತ ನೋಡಬೇಕು. Read the 4 statements. The resistance of intrinsic semiconductors decrease with the increase of temperature. It is the true statement because semiconductor devices or semiconductor materials are the materials having negative temperature coefficient of resistance. Temperature ಜಾಸ್ತಿ ಆದಾಗೆ resistance ಕಮ್ಮಿ ಆಗ್ತದೆ. Thus, statement is true. Doping of pure silicon with the trivalent impurities gives p-type semiconductor. The second statement given is also true. A PN junction can act as a semiconductor diode, or the other name of PN junction itself is semiconductor diode. So, the fourth option is also right. Just you see the third statement, the majority carriers in N-type semiconductors are holes. It is a wrong statement. Which is a wrong statement because in N-type semiconductor, N means negative, majority charge carriers are free electrons. So, in N-type semiconductor, majority charge carriers are electrons. So, the option C is the right answer. Now, we move on to next question. Read the question carefully. Consider the following statements A and B and identify the correct choice of the given answer. ಎರಡು ಸ್ಟೇಟ್ಮೆಂಟ್ ಅನ್ನು ಕೊಟ್ಟಿದ್ದಾರೆ. ಎರಡೂ ಸ್ಟೇಟ್ಮೆಂಟ್ ಅನ್ನು ಸರಿಯಾಗಿ ಓದಿಕೊಂಡು ಕೊಟ್ಟ 4 ಆಪ್ಷನ್ ಅಲ್ಲಿ ಯಾವುದು ಸರಿ ಅಂತ ಟಿಕ್ ಹಾಕಬೇಕು. Just you see, a Zener diode is always connected in reverse bias. Zener diode is a special purpose diode used as voltage regulator. To construct voltage regulator by using Zener diode, it is always connected in reverse bias. So, this is right. The potential barrier of PN junction lies between 0.1 to 0.3 volt approximately. See, potential barrier of germanium diode. The PN junction is made of germanium, then the barrier potential is nearly 0.3 volt. If it is made of silicon diode, if the diode is made of by adding impurities on either side for a silicon, then the resulting diode is called silicon diode. In silicon diode, the potential barrier is about 0.7 volt. As they didn't give the PN junction is of which type, the given statement is wrong. For germanium diode, potential barrier is 0.3 volt. For silicon diode, potential barrier is 0.7 volt. Here, they didn't mention about the type of the semiconductor diode. So, the second statement is wrong. First statement, A is right, B is wrong. So, option C is the right answer. So, option C. Now, we move on to question number 5. See, question number 5 is this. P-type semiconductor is formed when? P-type semiconductor is formed when they are given 4 options. Arsenic impurity is mixed with silicon. Aluminium impurity is mixed with silicon. Boron is mixed with germanium. And phosphorus impurity is mixed with germanium. We want P-type semiconductor. P-type semiconductor is formed only when pure semiconductor plus trivalent impurity atom. Here, pure semiconductor, silicon is pure semiconductor, germanium is also pure semiconductor. But trivalent impurity atoms examples are aluminum is trivalent, boron is also trivalent, resulting p-type semiconductor. So option B and C both are right. B and C both are right. So option C is the right answer. ಗೊತ್ತಾಗ್ತಾ ಇದೆಯಾ ನೋಡಿ, ಅಲ್ಯೂಮಿನಿಯಂ ಅನ್ನ ಸಿಲಿಕಾನಿಗೆ ಆಡ್ ಮಾಡಿದರೆ ಪಿ ಟೈಪ್ ಸೆಮಿಕಂಡಕ್ಟರ್ ಸಿಗ್ತದೆ. ಯಾಕಂದ್ರೆ ಅಲ್ಯೂಮಿನಿಯಂ ಈಸ್ ಟ್ರೈವೆಲೆಂಟ್, ಸಿಲಿಕಾನ್ ಈಸ್ ಪ್ಯೂರ್ ಸೆಮಿಕಂಡಕ್ಟರ್. ಸಿಮಿಲರ್ಲಿ boron added to germanium, here boron is trivalent, germanium is pure semiconductor resulting p type. So both cases B and C, option C is the right answer. Now we move on to next question. Just you see, in a PN junction diode not connected to any circuit, which statement is true? PN junction diode not connected to any circuit means it is unbiased diode. The diode is not connected to external voltage. In that case, which statement is true? Here, the potential is same everywhere. It is wrong because during the formation of PN junction, there is a potential barrier across the junction, that is 0.3 volt for germanium diode, 0.7 volt for silicon diode. So potential is not same. P type is higher potential than the N type side. It is also wrong because if this is a PN junction, this is P type, N type, a small amount of negative potential is existing across P side, across the junction, and N side, a small amount of positive potential exists due to immobile impurity ions. Here we have trivalent immobile ions act as negative charges, pentavalent donor ions act as positive charges. Due to this layer of immobile impurity ions across the junction, a potential exists across the junction called barrier potential. Due to that potential, there is an electric field from N side to P side. There is an electric field from N side to P side. That electric field causes drifting of minority carriers in reverse bias. Causes drifting of minority carriers in reverse bias. So, there is an electric field in the junction directed from N type side to the P type side is the right answer. Just you see the explanation. See, at junction a potential barrier and depletion layer is formed with N side at higher potential and P side is at lower potential. N side ಅಲ್ಲಿ pentavalent impurity ions ಇರುವುದರಿಂದ, immobile ions ಇರುವುದರಿಂದ ಅಲ್ಲಿ higher potential ಇರ್ತದೆ near the junction, and P side ಅಲ್ಲಿ trivalent impurity ions ಇರುವುದರಿಂದ, acceptor impurity ions ಇರುವುದರಿಂದ negative terminal ಇರ್ತದೆ. The potential barrier value is 0.3 volt for germanium diode, 0.7 volt for silicon diode. Due to this barrier potential, there exists an electric field across the junction from N side to P side. Just you see the diagram here. Say this. This is the electric field across the junction. Now we move on to the next question. Question number 7. Just you see the circuit. In the circuit, if the forward voltage drop for the diode is 0.5 volt, forward voltage drop, that means when electric current flows through the diode, due to the forward resistance, there is voltage drop across the junction. That voltage drop is called forward voltage drop. For the diode is 0.5 volt. the current will be. Just you see here, we want to find current, I. What we have to do is, current will be. See here, they given resistance R. Find out the voltage across the resistance. Here, total voltage applied is 8. 8 minus 0.5 becomes 7.5 volt. If this you take it as V, R is given, V by R will give I. 7.5 volt by 2.2 kilo ohm will give rise to 3.4 milliampere. 7.5 volt divided by 2.2 kilo ohm, kilo goes to the numerator, becomes milli. 7.5 by 2.2 is nearly 3.4. See, the voltage drop across the resistance 8 minus 0.5, 7.5 volt. Therefore, the current I is equal to V by R is 3.4 milliampere. Now you see the graphical question. Question number 8. The IV characteristics of PN junction diode is shown below. Current voltage characteristics of PN junction diode is as shown in the figure. The approximate dynamic resistance of PN junction when a forward bias volt of 2 volt is applied. We know resistance is nothing but, forward dynamic resistance is nothing but change in voltage by change in current. What is the change in voltage? 2.1 minus 2, that is 0.1. What is the change in current? 800 minus 400 milli. That is 0.1 by 400 milli. 0.1 by 400 milli means 0.1 by 0.4 ampere. Voltage by current is resistance. 0.25 ohm is the right answer. 0.25 ohm is the right answer. Dynamic resistance means, dynamic forward resistance means change in forward voltage to the corresponding change in forward current. The ratio is called dynamic forward resistance. Just we see the solution. R is equal to delta V by delta I. The value works out to be 0.25 ohm. Now we move on to question number 9. It is also a graphical question. Very important question. The temperature dependence of resistivity of a semiconductor is represented as. So, we know as temperature increases, in case of semiconductor, resistance decreases. The decrease is exponential in nature, so the option C is the right answer. Option C is the right answer. With the rise in temperature, resistivity of semiconductors decreases exponentially. See, the next question. A diode is connected to 220 volt AC in series with a capacitor as shown in the figure. They given 220 volt, the voltage is RMS in nature. Root means square value in nature. The voltage across the capacitor is, we know, as a single diode is used, it acts as half wave rectifier. In case of half wave rectifier, output of half wave rectifier is maximum value divided by 2, because only one half cycle of AC is converted into DC. So, V output is equal to V naught by 2, peak value divided by 2. What is the value? Peak value, they given Vrms. So, peak value becomes 220 root 2 by 2. Because we know V naught, peak value is nothing but RMS value into root 2. If you simplify, we get output as 220 by root 2, because this 2 right root 2, 1 root 2 cancels. Just we see the solution. The diode D will conduct for positive half cycle of AC supply, forward biased. For negative half cycle AC supply, reverse bias, the diode does not conduct. Forward bias alli matra conduct ಮಾಡ್ತದೆ, reverse bias alli conduct ಮಾಡೋದಿಲ್ಲ. Output would be half wave rectified, and for half wave rectified output, V output is equal to V naught by 2, 220 root 2 by 2, 220 by root 2. Option D is the right answer. Next question, for germanium crystal, the forbidden energy gap in joules. We know for germanium, energy gap in electron volt is 0.7 eV. Convert into joule, 0.7 into 1.6 into 10 power minus 19. Ten power minus 19. 1.6 into 0.7, 1.12 into 10 power minus 19 is the right answer. Suppose the question is for silicon. Then for silicon, what is the value of energy gap? Energy gap is 1.1 eV for silicon. So, if I convert this into joules, it works out to be 1.76 into 10 power minus 19. So, for silicon, it is the option B is the right answer. But in the question they asked about germanium, option A is the right answer. For germanium, 0.7 electron volt convert into joule by multiplying 1.6 into 10 power minus 19. This is also diagram, energy band diagram based question. Which of the following energy band diagram shows the N-type semiconductor? ಇದರಲ್ಲಿ ಯಾವುದು N type semiconductor ಅಂತ ಕೇಳ್ತಾ ಇದ್ದಾರೆ. Which is N-type semiconductor here? Here, in case of N-type semiconductor, the energy level of impurity atom lies just below the conduction band. Energy level of impurity atom added lies just below the conduction band. So, the right option for this is option B. Suppose energy band diagram of p-type semiconductor looks like this. p-type semiconductor nelladru kelidre conduction band, valence band, energy level is just above the valence band. Impurity energy level. This is for p-type semiconductor. So, for this question, option B is the right answer. Keep in mind, in case of energy band, always conduction band lies above the valence band. Conduction band lies above the valence band. In n-type semiconductor, impurity energy level lies just below the conduction band. We move on to the next question. A germanium specimen is doped with aluminium. Just you see here, a germanium specimen is doped with aluminium. Clearly, germanium is a pure semiconductor, aluminium is a trivalent impurity atom. Aluminium is a trivalent impurity atom. So the resulting semiconductor is p-type. Adu gottagtade first ge. Sariya? So it is an extrinsic semiconductor. Here they given concentration of acceptor atoms is 10 power 21 atoms. We already mentioned during the synopsis, in case of extrinsic semiconductor, p-type semiconductor, number of holes is equal to number of acceptor atoms is equal to 10 power 21 that they given. In addition to that, the intrinsic concentration of electron hole pairs, Ni, is also given. 10 power 19. Their question is, the concentration of electrons is how much? Ne is to calculate. How to find this? How to find Ne? What you have to do is, we know for extrinsic semiconductor, Ne into Nh is equal to Ni square. Use this. Ni square. If I use this, we get the answer 10 power 17. Just we see here. Ni square is equal to Nh into Ne. 10 power 19 square is equal to 10 power 21 into Ne. So Ne becomes 10 power 17. Option A is the right answer. Option A is the right answer. Now we move on to next question. See, read the question carefully. The diode used in the circuit shown in the figure has a constant voltage drop of 0.5 volt. Diode current ಅನ್ನು ಪಾಸ್ ಮಾಡುವಾಗ 0.5 volt voltage drop ಆಗ್ತದೆ. At all the currents and maximum power rating of the diode is 100 milliwatt. ಅದು ಪವರ್ ಕನ್ಸ್ಯೂಮ್ ಮಾಡೋದು ಎಷ್ಟು ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ P 100 milliwatt. What should be the value of resistance R connected in series with the diode for obtaining the maximum current? So first we calculate current across the diode. We know P is equal to V into I, right? ಇದನ್ನು ಕಲ್ತಿದ್ದೇವೆ ಕರೆಂಟ್ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ ಚಾಪ್ಟ್ರಲ್ಲಿ. P is equal to V into I. So I is equal to P by V. Calculate current. Power 100 milliwatt, that is nothing but 0.1 watt by 0.5. 0.5 is the voltage drop across the diode. So I works out to be 0.2 ampere. I ಸಿಕ್ತು. I is 0.2 ampere. Now, the voltage drop across the resistor is 0.5. V is equal to 1.5 minus 0.5. 1.5 minus 0.5 how much? 1 volt. V we get. R is equal to V by 1 by 0.2, 5 ohm. R is equal to see, the current through the circuit I is equal to P by V, 100 into 10 power minus 3 by 0.5, 0.2 ampere. Voltage drop across the resistance 1.5 minus 0.5, 1 volt. Therefore, the resistance to be connected in series with the diode value is 1 by 0.5 or 1 by 0.2, 5 ohm. Option B is the right answer. Now we move on to next question. Question number 15. In the following circuit, PN junction diode D1, D2, D3 are ideal. ಮೂರು ಡಯೋಡ್ ಇದೆ, D1, D2, D3, ಅವು ಮೂರು ಐಡಿಯಲ್ ಡಯೋಡ್. What do you mean by ideal diode is, during forward bias, resistance offered is 0 ohm. During reverse bias, resistance is infinity. So, forward bias ಅಲ್ಲಿ ಡಯೋಡ್ ಇದ್ರೆ resistance 0, reverse bias ಅಲ್ಲಿ ಡಯೋಡ್ ಇದ್ರೆ resistance infinite. Or during forward bias, diode is act as short circuit. During reverse bias, diode act as open circuit. So, in the following circuit, PN junction diode D1, D2, D3 are ideal for the following potential A and B. The correct increasing order of the resistances between A and B will be A ಮತ್ತೆ B ನಡುವೆ increasing order of resistance ಹೇಗಿರ್ತದೆ ಯಾವಾಗ? When the potential at A and B are given as first case minus 10 minus 5, ಇಲ್ಲಿ minus 10 ವೋಲ್ಟ್ ಕೊಡ್ತಾರೆ, ಇಲ್ಲಿ minus 5 ವೋಲ್ಟ್ ಕೊಡ್ತಾರೆ, ಆಗ ರೆಸಿಸ್ಟೆನ್ಸ್ ಎಷ್ಟಿರ್ತದೆ ಒಂದನೇ ಕೇಸ್ ನೋಡೋದು. ಅದೇ ರೀತಿ ಸೆಕೆಂಡ್ minus 5 ವೋಲ್ಟ್ ಕೊಡೋದು, ಇಲ್ಲಿ minus 10 ವೋಲ್ಟ್ ಕೊಡೋದು, ಆಗ ರೆಸಿಸ್ಟೆನ್ಸ್ ಎಷ್ಟಿರ್ತದೆ ನೋಡೋದು. ಥರ್ಡ್ ಕೇಸಲ್ಲಿ ಇಲ್ಲಿ minus 4 ವೋಲ್ಟ್ ಕೊಡೋದು, ಇಲ್ಲಿ minus 8 ವೋಲ್ಟ್ ಕೊಡೋದು, ಆಗ ರೆಸಿಸ್ಟೆನ್ಸ್ ಎಷ್ಟಿರ್ತದೆ ನೋಡೋದು. ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ಅಲ್ಲಿ ರೆಸಿಸ್ಟೆನ್ಸ್ ಆಫ್ ದ ಡಯೋಡ್ ಇಸ್ 0. ರಿವರ್ಸ್ ಬಯಾಸ್ ಇಲ್ಲಿದ್ರೆ ರೆಸಿಸ್ಟೆನ್ಸ್ ಆಫ್ ದ ಡಯೋಡ್ ಇಸ್ ಇನ್ಫಿನಿಟಿ ಆರ್ ಓಪನ್ ಸರ್ಕ್ಯೂಟ್. ನಾವು ವಿ ಕನ್ಸಿಡರ್ ದ ಫಸ್ಟ್ ಕೇಸ್. ಈ ಕೇಸನ್ನು ತಗೊಳ್ಳುವ. ಸೊ ಎ minus 10, B minus 5. A is more negative than B. A more negative ಇದೆ ಬಿಗೆ. ಆದ್ದರಿಂದ ಯಾವ ಡಯೋಡ್ ಫಾರ್ವರ್ಡ್ ಬಯಾಸಲ್ಲಿದೆ, ಯಾವ ಡಯೋಡ್ ರಿವರ್ಸ್ ಬಯಾಸಲ್ಲಿದೆ ಅಂತ ನೋಡುವ. D1 and D3. D1 and D3, see, P side connected to negative potential, N side connected to higher potential than this. minus 10ಗೆ ಹೋಲಿಸಿದ್ರೆ minus 5 ಪಾಸಿಟಿವ್. ಅರ್ಥ ಆಗ್ತಾ ಇದೆಯಾ? minus 10ಗೆ ಹೋಲಿಸಿದ್ರೆ minus 5 is more. So, diode D1 and D3 are in reverse bias. Whereas, diode D2 is in forward bias. ಹಾಗಾಗಿ ರಿವರ್ಸ್ ಬಯಾಸ್ ಅಲ್ಲಿ ಇನ್ಫೈನೈಟ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಇರೋದ್ರಿಂದ ಇದನ್ನು ಬಿಡಿ, ಟೋಟಲ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಲೆಕ್ಕ ಹಾಕಿ ಎ ಮತ್ತು ಬಿ ನಡುವೆ ಎಷ್ಟಾಗ್ತದೆ? R by 4, R by 4. All the three are in series. Effective resistance becomes R by 4, R by 4, R, 3R by 2 or 1.5 R. ಯಾವಾಗ ಇದು? In case of minus 10 and minus 5 volt given at A and B. Now, you give voltage ಅನ್ನು ಚೇಂಜ್ ಮಾಡಿ. ಇಲ್ಲಿ minus 5 volt ಕೊಡಿ, minus 10 volt B ಗೆ ಕೊಡಿ. ಆಗ ಡಯೋಡ್ನ ಬಯಾಸಿಂಗ್ ಕೂಡ ಚೇಂಜ್ ಆಗ್ತದೆ. ಏನಾಗ್ತದೆ? D1 and D2 are in forward bias. D2 reverse bias. ಆದ್ದರಿಂದ the resistance works out like this. R by 4, R by 4. ಮೇಲಿನ R ಯಾವುದು? D1 ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ಅಲ್ಲಿದೆ. ಕೆಳಗಿನ R ಯಾವುದು? ಲಾಸ್ಟ್ ಡಯೋಡ್ ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ಅಲ್ಲಿದೆ. ಮಧ್ಯದ ಡಯೋಡ್ ರಿವರ್ಸ್ ಬಯಾಸ್. ಇದನ್ನು ಬಿಟ್ಟುಬಿಡಿ ಈಗ. ಯಾಕೆ? minus 5 volt, minus 10 volt. D1 and D2 are in forward bias. ಶಾರ್ಟ್ ಸರ್ಕ್ಯೂಟ್ ಕರೆಂಟನ್ನು ಪಾಸ್ ಮಾಡ್ತದೆ. ಮಧ್ಯದ ಡಯೋಡ್ ರಿವರ್ಸ್ ಬಯಾಸ್ ಅಲ್ಲಿದೆ, ಕರೆಂಟನ್ನು ಪಾಸ್ ಮಾಡೋದಿಲ್ಲ. ಓಪನ್ ಸರ್ಕ್ಯೂಟ್. ನೆಗ್ಲೆಕ್ಟ್ ದಿಸ್ ರೆಸಿಸ್ಟೆನ್ಸ್. ಸರ್ಕ್ಯೂಟ್ ಬಿಡಿಸಿದ್ದೇನೆ. ಇದನ್ನು ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿದರೆ R parallel R is R by 2. R by 4 plus R by 2 plus R by 4 is R. ಸೆಕೆಂಡ್ ಕೇಸಿನ ರೆಸಿಸ್ಟೆನ್ಸ್ ಸಿಕ್ತು R. ಫಸ್ಟ್ ಕೇಸಲ್ಲಿ ರೆಸಿಸ್ಟೆನ್ಸ್ 3R by 2. ಥರ್ಡ್ ಕೇಸ್ ನೋಡಿ, minus 4 volt, minus 12 volt, ಸೇಮ್ ಆಸ್ minus 5, minus 10. ಯಾಕಂದರೆ ವ್ಯಾಲ್ಯೂ ಮಾತ್ರ ಚೇಂಜ್ ಆಗಿದೆ ಬಿಟ್ಟರೆ minus 5 ಇದನ್ನು minus 4 ಮಾಡಿದ್ದಾರೆ, minus 10 ಇದನ್ನು minus 8 ಮಾಡಿದ್ದಾರೆ. ಬಯಾಸಿಂಗ್ ಕಂಡೀಷನ್ ದರ್ ಈಸ್ ನೋ ಚೇಂಜ್. ನೋ ಚೇಂಜ್ ಇನ್ ದ ಬಯಾಸಿಂಗ್ ಕಂಡೀಷನ್ ಆಫ್ ದ ಡಯೋಡ್ ಡ್ಯೂ ಟು ದ ವೋಲ್ಟೇಜ್ minus 4 and minus 2, minus 8, ಸೇಮ್ ಆಸ್ ದ ಸೆಕೆಂಡ್ ಕೇಸ್. ಆದ್ದರಿಂದ ಥರ್ಡ್ ಕೇಸಲ್ಲಿ ಕೂಡ ರೆಸಿಸ್ಟೆನ್ಸ್ ಇಷ್ಟೇ ಬರ್ತದೆ. ಇನ್ಕ್ರೀಸಿಂಗ್ ಆರ್ಡರ್ಲಿ ಹೇಳಬೇಕು ಅಂತ ಹೇಳಿದ್ದಾರೆ. ಸೊ ಆಪ್ಷನ್ ಸಿ ಇಸ್ ದ ರೈಟ್ ಆನ್ಸರ್. ಬಿಕಾಸ್ ಸೆಕೆಂಡ್ ಕೇಸ್ ಥರ್ಡ್ ಕೇಸಲ್ಲಿ ರೆಸಿಸ್ಟೆನ್ಸ್ ಬಂದಿದೆ R ಮತ್ತು R. ಫಸ್ಟ್ ಕೇಸಲ್ಲಿ ಎಷ್ಟು ಬಂದಿದೆ? 3R by 2. ಸೊ ಥರ್ಡ್ ಆಪ್ಷನ್ ಹೋಲ್ಡ್ಸ್ ಗುಡ್ ಫಾರ್ ದಿಸ್. ಥರ್ಡ್ ಆಪ್ಷನ್ ಹೋಲ್ಡ್ಸ್ ಗುಡ್ ಫಾರ್ ದಿಸ್. ದಿಸ್ ಪ್ರಾಬ್ಲಮ್ ಈಸ್ ವೆರಿ 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 ಇಂಪಾರ್ಟೆಂಟ್. Here you keep in mind, forward biasing of the diode means short circuit, reverse biasing open circuit for ideal diode. Just we move on to the solution. See, ಹೇಗೆ ಸೊಲ್ಯೂಷನ್ ಬಂದಿದೆ ಅಂತೆಲ್ಲ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಿದ್ದೇನಲ್ಲ, ಅದನ್ನು ಇಲ್ಲಿ ಹೇಳಿದು. ಸೊ ಇನ್ ಫಸ್ಟ್ ಕೇಸ್ minus 10, minus 5 ಕೊಡುವಾಗ D1, D3 ರಿವರ್ಸ್ ಬಯಾಸಲ್ಲಿ ಇರ್ತದೆ, D2 ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್. ಮಧ್ಯದ ರೆಸಿಸ್ಟೆನ್ಸ್ ಮಾತ್ರ ಕೌಂಟ್ ಮಾಡೋದು. ಟೋಟಲ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಬಿಕಮ್ಸ್ 3R by 2. ನೆಕ್ಸ್ಟ್, ಫಾರ್ ಸೆಕೆಂಡ್ ಆ್ಯಂಡ್ ಥರ್ಡ್ ಕೇಸ್, ಫಸ್ಟ್ ಆ್ಯಂಡ್ ದ ಲಾಸ್ಟ್ ಡಯೋಡ್ಸ್ ಆರ್ ಇನ್ ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್, ದ ಮಿಡಲ್ ಡಯೋಡ್ ಇಸ್ ಇನ್ ರಿವರ್ಸ್ ಬಯಾಸ್. ಅದನ್ನು ತೆಗೆದುಬಿಡಿ, ಟೋಟಲ್ ರೆಸಿಸ್ಟೆನ್ಸನ್ನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ ವ್ಯಾಲ್ಯೂ ಸಿಗ್ತದೆ. So option C is the right answer. Question number 16. Now we move on to question number 16. The circuit shown in the following figure contains two diodes D1 and D2 with forward resistance of 50 ohm. ನೋಡಿ, ಇದು ಐಡಿಯಲ್ ಡಯೋಡ್ ಅಲ್ಲ. Here the question itself they given forward resistance of 50 ohm, infinite backward resistance. Reverse bias alidre resistance infinite anta kottidare. If the battery voltage is 6 volt, the current through 100 ohm resistance in ampere is. See here, by seeing the circuit we can make out as this side is positive, this is negative, diode D1 is in forward bias, diode D2 is in reverse bias, right? Because line N side connected to positive terminal, triangle P side connected to negative terminal. So, ಮಧ್ಯದ ಡಯೋಡ್ ಇದೆಯಲ್ಲ ಇದು ರಿವರ್ಸ್ ಬಯಾಸ್ ಅಲ್ಲಿದೆ. ರಿವರ್ಸ್ ಬಯಾಸ್ ಅಲ್ಲಿ ಹೇಳಿದ್ದಾರೆ ಇನ್ಫೈನೈಟ್ ಬ್ಯಾಕ್ವರ್ಡ್ ರೆಸಿಸ್ಟೆನ್ಸ್, ಓಪನ್ ಸರ್ಕ್ಯೂಟ್ ಬಿಟ್ಬಿಡಿ ಅದನ್ನು, ನೆಗ್ಲೆಕ್ಟ್. ಆ್ಯಂಡ್ ಫಾರ್ವರ್ಡ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಇಲ್ಲಿ ಝೀರೋ ಅಲ್ಲ, ಶಾರ್ಟ್ ಅಲ್ಲ, ಇದು ರೆಸಿಸ್ಟೆನ್ಸ್ ಕೊಟ್ಟಿದ್ದಾರೆ, ಇದು ಇಂಪಾರ್ಟೆಂಟ್, 50 ಓಮ್ ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ, ಸರಿಯಾ? ಸೊ ಫೈಂಡ್ ಔಟ್ ದ ಟೋಟಲ್ ರೆಸಿಸ್ಟೆನ್ಸ್ 50, 150, 100. ಇಲ್ಲೊಂದು ಸೀರೀಸ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಕೊಟ್ಟಿದ್ದಾರಲ್ಲ, ಇದು ಓಪನ್ ಆಗಿದೆ, 150 + 50, 200, 300. What they want? Current I is equal to V by R total. That is 6 by 300. ಹೇಗೆ ಬಂತು 300? ಇಲ್ಲೊಂದು 100 ಓಮ್, ಇಲ್ಲೊಂದು 150 ಓಮ್, ಇಲ್ಲೊಂದು 50 ಓಮ್ ಆ್ಯಡ್ ಮಾಡಿ, ಟೋಟಲ್ ಎಷ್ಟಾಗ್ತದೆ? ಟೋಟಲ್ ಬಿಕಮ್ಸ್ 300. 6 by 300. Answer is 0.02 ampere. 0.02 ampere. Option B is the right answer. Just you see the solution. According to the given polarity, diode D1 is forward biased while D2 is reverse biased. D1 forward bias ಅಲ್ಲಿದೆ, D2 reverse bias ಅಲ್ಲಿದೆ. ಆದ್ದರಿಂದ ಏನಾಗ್ತದೆ, ರಿವರ್ಸ್ ಬಯಾಸ್ ಅಲ್ಲಿ ಇನ್ಫೈನೈಟ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ, ಆ ಬ್ರಾಂಚನ್ನು ಓಪನ್ ಮಾಡಿ, ಟೋಟಲ್ ರೆಸಿಸ್ಟೆನ್ಸ್ ನೋಡಿ V by R ಮಾಡಿದರೆ I ಸಿಗ್ತದೆ. ಮೂವ್ ಆನ್ ಟು ದ ನೆಕ್ಸ್ಟ್ ಕ್ವಶನ್. ಫೈಂಡ್ voltage across A and B. VAB, this is the point A, this is the point B. Here, just you see the circuit, this is positive terminal, negative terminal, positive terminal is connected to P, negative terminal is connected to N, the diode is in forward bias. Forward bias means assume that the diode is ideal, make it short, direct connect ಮಾಡಿ ಹೀಗೆ. ಈಗ the circuit becomes simple. ಹೀಗಾಯ್ತು, ಇದು 10. Just you see the total resistance, 10 parallel 10 becomes 5 ohm, right? 10 parallel 5 ohm, total resistance of the circuit 15 ohm, 10 plus 5, 15 ohm. ವೋಲ್ಟೇಜ್ ಕೊಟ್ಟಿದ್ದಾರೆ 30 ವೋಲ್ಟ್, ಕರೆಂಟ್ ನೋಡ್ಕೊಳ್ಳಿ, ಐ ಎಷ್ಟಾಗ್ತದೆ, 30 by 15, 2 ampere current. What they want? Voltage across AB is nothing but voltage across this parallel combination. Voltage across AB is nothing but voltage across parallel combination. That is V is equal to I into RP. ಎಷ್ಟಾಗ್ತದೆ? 2 into 5 ohm, 10 volt. Voltage across parallel combination is 10 volt. Just we see the solution. Just you see the circuit. See, as the diode is forward bias, short ಮಾಡಿ, simplify ಮಾಡಿ, RP ನೋಡಿ, total resistance ನೋಡಿ, ಇದು current. This is nothing but current into resistance of the parallel combination. We will give 10 volt. Next, move on to next question. The depletion layer in a silicon diode is 1 micrometer. Width of the depletion layer is given 1 micrometer. And the knee volt potential is 0.6 volt. Then knee potential is 0.6 volt. Then the depletion layer, electric field in the depletion layer. It is direct. The relation between electric field and potential E is equal to V by D. Calculate 0.6 by 1 micrometer works. 0.6 by 1 micrometer, 0.6 into 10 power 6 or 6 into 10 power 5. It's a direct question. 6 into 10 power 5 volt. Next question. In the half-wave rectifier shown, which of the following waveforms is true for the output across C and D? This is direct theory based question. Half-wave rectifier na output waveform gottidre aaytu ashte. Clearly, as the circuit is half-wave rectifier, only one diode is there. During positive half cycle, diode is in on position or it produces output voltage. During negative half cycle, diode is at off state or in reverse bias. So, the output is like this. Because during positive half cycle, output is present, negative half cycle, output is missing. Next positive half cycle, once again output is present, negative half cycle is missing. Only one half cycle of AC is converted into DC. Option B is the right answer. Now we move on to question number 20. A diode having potential difference of 0.5 volt across its junction, which does not depend on the current, is connected in series with a resistance of 20 ohm across the source. If 0.1 ampere passes through the resistance, then what is the voltage of the source? Source voltage ಎಷ್ಟು ಅಂತ ನೋಡಬೇಕು. Just you see, say this is the condition. A diode having potential difference of 0.5, potential drop 0.5 volt. This is 20 ohm. 0.1 ampere is the current. V is to find. Voltage of the source is nothing but voltage across the resistor plus voltage drop across the diode. That is I into R plus 0.5. Into 0.1, 2 plus 0.5, 2.5 volt is the right answer. 2.5 volt is the right answer. Just we check the answer. See, this is the diode, resistor, battery. This is to find ಇಲ್ಲಿ ವೋಲ್ಟೇಜನ್ನು ನೋಡಬೇಕು, ವಿ ಡ್ಯಾಶ್ ಅಂತ ತಗೊಂಡಿದ್ದೇವೆ. ಇಲ್ಲಿ ವೋಲ್ಟೇಜನ್ನು ವಿ ಅಂತ ತಗೊಂಡದ್ದು, ಇದು 0.5 ಅಂತ ಕೊಟ್ಟಿದ್ದಾರೆ. ಸಿಂಪಲ್, ವಿ ಡ್ಯಾಶ್ ಇಸ್ ಈಕ್ವಲ್ ಟು ವಿ ಪ್ಲಸ್ ಐ ಆರ್. ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಿದರೆ ಆ್ಯಡ್ ಮಾಡಿದರೆ ಸಿಗ್ತದೆ. ಇಟ್ಸ್ ಅ ಡೈರೆಕ್ಟ್ ಆಪ್ಷನ್ ಸಿ ಇಸ್ ದ ರೈಟ್ ಆನ್ಸರ್. ಕ್ವೆಶ್ಚನ್ ನಂಬರ್ 20. The combination of gates shown in the figure below produces. See, in the synopsis, we already explained that NAND gate and NOR gates are universal gates. NAND ಮತ್ತು NOR ಗೇಟನ್ನು ಯೂನಿವರ್ಸಲ್ ಗೇಟ್ ಅಂತ ಹೇಳ್ತೇವೆ. ಯಾಕಂದರೆ by using those gates it is possible to construct the basic logic gates OR, AND NOT. Here the application of the same is given in this. See, this is there are 3 NAND gates. 3 NAND gate ಅನ್ನು ಕನೆಕ್ಟ್ ಮಾಡಿದ್ದಾರೆ. ಇದು A bar, B bar, Y. So we know Y output NAND gate already ನಮಗೆ ಗೊತ್ತಿದೆ. If input is A and B, output is A, B bar. ಇಲ್ಲಿ ಇನ್ಪುಟ್ A ಬಾರ್ B ಬಾರ್ ಆದ್ದರಿಂದ ಔಟ್ಪುಟ್ ಏನಾಗ್ತದೆ? A ಬಾರ್ B ಬಾರ್ whole bar, which is nothing but by using De Morgan's theorem, A bar bar plus B bar bar, complement of complement is A plus B. A plus B is nothing but OR gate. A plus B is nothing but OR gate. Once again I repeat, see here, if A and B are the inputs of NAND gate, output is AB bar. Here, instead of A we have A bar, instead of B we have B bar. Y is equal to A bar, B bar complement. This is written using De Morgan laws. De Morgan's law. A bar, B bar complement is nothing but A bar bar plus B bar bar. Bar complement of complement is the same. So A plus B, or which is the output of OR gate. Similarly, instead of NAND gate ಬದಲಿಗೆ ಸರ್ಕ್ಯೂಟ್ ಅನ್ನು ಹೀಗೆ ಕೊಟ್ಟಿದ್ದಾರೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. NOR gate ಕೊಟ್ಟಿದ್ದಾರೆ. This is, here all the 3 NAND gates are replaced by NOR gate. ಈ NAND gate ಬದಲಿಗೆ NOR gate ಹಾಕಿದರೆ ಆಗ ಏನಾಗ್ತದೆ ನೋಡಿ. ಇಲ್ಲಿ ನಮಗೆ ಗೊತ್ತಿದೆ, ಒಂದು NOR gate ಇದ್ರೆ ಏನು A ಪ್ಲಸ್ B ಕಾಂಪ್ಲಿಮೆಂಟ್ ಅಂತ ಬರಿತೇವೆ. ಇಲ್ಲಿ ಇದೇನಾಗ್ತದೆ? A ಪ್ಲಸ್ ಬಿ, ಎ ಬದಲಿಗೆ ಏನಿದೆ? ಬಾರ್ ಬಾರ್ ಕಾಂಪ್ಲಿಮೆಂಟ್ ಔಟ್ಪುಟ್. ಹಿಯರ್ ಆಲ್ಸೋ ವಿ ಯೂಸ್ ಡಿ ಮಾರ್ಗನ್ಸ್ ಲಾ such that A bar bar into B bar bar, which is AB, this is equivalent to AND gate. If the same circuit, ಅದೇ ಸರ್ಕ್ಯೂಟ್ ಅನ್ನು NOR ಗೇಟ್ ಅಲ್ಲಿ ಕೊಟ್ಟರೆ ಆಗ ಆ ಸರ್ಕ್ಯೂಟ್ ಏನಾಗ್ತದೆ ಅಂದರೆ ಈಕ್ವಲೆಂಟ್ ಟು ಆ್ಯಂಡ್ ಗೇಟ್. ನೆನಪಿಟ್ಕೊಳ್ಳಿ, 3 NAND ಗೇಟನ್ನು ಈ ರೀತಿ ಕನೆಕ್ಟ್ ಮಾಡಿದರೆ ಇಟ್ ಈಸ್ ಈಕ್ವಲೆಂಟ್ ಟು ಆರ್ ಗೇಟ್. ಇದರ ಆನ್ಸರ್ ಆರ್ ಗೇಟ್. ಅದೇ ಈ 3 NAND ಗೇಟ್ ಬದಲಿಗೆ ನಾರ್ ಗೇಟನ್ನು ಅದೇ ರೀತಿ ಕನೆಕ್ಷನ್ ಮಾಡಿದರೆ ಇಟ್ ಈಸ್ ಈಕ್ವಲ್ ಟು ಆ್ಯಂಡ್ ಗೇಟ್. ಕ್ಲಿಯರ್? See, by De Morgan's law, y is equal to, ಇಲ್ಲಿ ಔಟ್ಪುಟ್ a ಬಾರ್ b ಬಾರ್ ಹೋಲ್ ಬಾರ್. ಇದು ಡಿ ಮಾರ್ಗನ್ಸ್ ಲಾ, ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ಬಂದದ್ದು ಡಿ ಮಾರ್ಗನ್ಸ್ ಲಾ. a ಪ್ಲಸ್ ಬಿ ವಿಚ್ ಈಸ್ ನಥಿಂಗ್ ಬಟ್ ಆರ್ ಗೇಟ್. ಆಪ್ಷನ್ ಬಿ ಈಸ್ ಅ ರೈಟ್ ಆನ್ಸರ್. ಅದೇ ಈ NAND ಗೇಟ್ ಬದಲಿಗೆ ನಾರ್ ಗೇಟನ್ನು ಕೊಟ್ಟರೆ ದ ಆನ್ಸರ್ ಈಸ್ ಆ್ಯಂಡ್ ಗೇಟ್. Now we move on to question number 22. 22nd. Which one is reverse biased? ಈ ಸರ್ಕ್ಯೂಟಲ್ಲಿ 4 ಡಯೋಡ್ ಕಂಡೀಷನ್ ಕೊಟ್ಟಿದ್ದಾರೆ, ಬೇರೆ ಬೇರೆ ಪೊಟೆನ್ಷಿಯಲ್ ವ್ಯಾಲ್ಯೂ ಕೊಟ್ಟಿದ್ದಾರೆ. ಅದರಲ್ಲಿ ಯಾವುದು ರಿವರ್ಸ್ ಬಯಾಸಲ್ಲಿದೆ ಅಂತ ನೋಡಬೇಕು. ರಿವರ್ಸ್ ಬಯಾಸ್ ಅಂದರೆ ನೆನ್ಪಿಟ್ಕೊಳ್ಳಿ, ಪಿ ಸೈಡ್ ಈಸ್ ಪಾಸಿಟಿವ್, ಪಿ ಸೈಡ್ ಈಸ್ ನೆಗೆಟಿವ್, ಎನ್ ಸೈಡ್ ಈಸ್ ಪಾಸಿಟಿವ್. ಎನ್ ಪ್ಲಸ್ಸಿಗೆ ಕನೆಕ್ಟ್ ಮಾಡಿದರೆ, ಪಾಸಿಟಿವ್ ಟರ್ಮಿನಲ್ ಆಫ್ ದ ಬ್ಯಾಟ್ರಿ ಕನೆಕ್ಟ್ ಮಾಡಿದರೆ ಅಥವಾ ಹೈಯರ್ ಪೊಟೆನ್ಷಿಯಲಿ ಕನೆಕ್ಟ್ ಮಾಡಿದರೆ, ಪಿ ಅನ್ನು ಲೋವರ್ ಪೊಟೆನ್ಷಿಯಲಿ ಕನೆಕ್ಟ್ ಮಾಡಿದರೆ ಆಗ ವಿ ಸೇ ದ ಡಯೋಡ್ ಈಸ್ ಇನ್ ರಿವರ್ಸ್ ಬಯಾಸ್. Just you see 15 volt, 10 volt, 15 is higher potential connected to P, 10 volt is lower potential connected to N, it is forward biased. This is not the answer. Now we see this, -5 connected to P, -10 connected to N, -5 is higher potential compared to -10, it is also forward bias. That is not the answer. Just you see the third one, -10 volt, the N side is connected to earth. Earth means 0 volt. Earthing means 0 volt. So, 0 is higher potential compared to -10. Agree? 0 is higher potential compared to -10. So, the diode C is in reverse bias. It is the answer. Now we see the fourth option. 10 volt is higher potential, -5 lower potential, it is also forward bias. We want reverse biased, answer is C. Only in option C, P side is more negative as compared to N side. See, here once again the statement type question. Consider the following statements A and B and identify the correct of the given answers. ಎರಡು ಸ್ಟೇಟ್ಮೆಂಟ್ ಕೊಟ್ಟಿದ್ದಾರೆ, ಎರಡು ಸ್ಟೇಟ್ಮೆಂಟನ್ನು ಸರಿ ಓದಿಕೊಂಡು ಕೊಟ್ಟ ಆಪ್ಷನಲ್ಲಿ ಯಾವ ಸರಿ ಆನ್ಸರ್ ಅಂತ ನೋಡಬೇಕು. ಸಿ ದ ಫಸ್ಟ್ ಸ್ಟೇಟ್ಮೆಂಟ್, the width of the depletion layer in PN junction diode increases in forward bias. Whether it is right or wrong. See, width of depletion layer during forward bias decreases. But the given width of depletion layer increases is wrong statement. Wrong statement. In an intrinsic semiconductor, Fermi energy level is exactly in the middle of the forbidden gap. Fermi energy level in case of pure semiconductor lies in the middle of the forbidden gap is a right answer. So, statement A is false, B is true, A false, B true, option C is the right answer. Just we check the answer. See here, in forward biasing of PN junction diode, width of depletion layer not increases, it must decrease. Then in intrinsic semiconductor, Fermi energy level is exactly in the middle of the forbidden gap is right. So option C is the right answer. Now we move on to the next question. See here, the waveform is given. Circuit kodlilla, digital circuit anna kodlilla, waveform anna kottidare. The given figure shows the waveforms for two inputs A and B and that for output Y of a logic circuit. You should name the logic circuit. Is waveform anna nodkondu ನೀವು logic circuit ಯಾವುದು ಅಂತ ಹೇಳಬೇಕು. Just you see, you divide this waveform into 4 parts. ಹೀಗೆ ಡಿವೈಡ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಸರಿಯಾ? ನೋಡಿ, A 0, B 0, I ಕೂಡ 0. 3 ಲೋ. ನೆಕ್ಸ್ಟ್ A 0, B ಸ್ವಲ್ಪ ಮೇಲಿದೆ ಅಂದರೆ ಹೈ ಅಂತ ಅರ್ಥ 1. ಔಟ್ಪುಟ್ ಇದು 0ನೇ, ಲೋ ಲೆವೆಲಲ್ಲೇ ಇದೆ. ಸರಿಯಾ? ಮೂರನೇ ಬನ್ನಿ, A1 B0 ಇದೆ, ಔಟ್ಪುಟ್ 0 ಇದೆ. ಲಾಸ್ಟ್ ಕೇಸಿಗೆ ಬನ್ನಿ, A ಹೈ ಇದೆ, B ಕೂಡ ಹೈ ಇದೆ, ಔಟ್ಪುಟ್ ಕೂಡ ಹೈ ಇದೆ. 1 1 is 1. I already told while explaining the important points, 1 1 is 1. If both inputs are 1, output is 1, the resulting logic circuit is AND gate. AND gate. Waveform ಅನ್ನು ಕೊಟ್ಟರೆ ಲಾಜಿಕ್ ಸರ್ಕ್ಯೂಟ್ ಯಾವುದು ಅಂತ ನೋಡೋದು. ಡಿವೈಡ್ ಮಾಡ್ಕೊಳ್ಳಿ. 0 to T1, A is 0, B is 0, Y is 0. Between T1 and T2, A low, B high, output is 0. ಅದೇ ರೀತಿ ಥರ್ಡ್ ಪಾರ್ಟಲ್ಲಿ, ಫೋರ್ತ್ ಪಾರ್ಟಲ್ಲಿ ನೋಡಿದರೆ ನಮಗೆ ಗೊತ್ತಾಗ್ತದೆ, ಫೋರ್ತ್ ಪಾರ್ಟಲ್ಲಿ ಎ ಮತ್ತು ಬಿ ಎರಡೂ ಕೂಡ ಹೈ ಇದೆ, ಆದ್ದರಿಂದ ಔಟ್ಪುಟ್ ಕೂಡ ಹೈ ಇದೆ. ದ ಔಟ್ಪುಟ್ ಈಸ್ ದ ಸರ್ಕ್ಯೂಟ್, ವೇವ್ ಫಾರ್ಮ್ ಈಸ್ ಕರೆಸ್ಪಾಂಡಿಂಗ್ ಟು ದ ಲಾಜಿಕ್ ಸರ್ಕ್ಯೂಟ್ ಆ್ಯಂಡ್ ಗೇಟ್. See, in the truth table type is given. Now we move on to next question. Which of the following gates will have an output of 1? ಇದರಲ್ಲಿ ಯಾವುದರ ಔಟ್ಪುಟ್ 1 ಅಂತ ಹೇಳಬೇಕು. ಫಸ್ಟಿಗೆ ನಿಮಗೆ ಈ ಗೇಟ್ಸನ್ನು ಯಾವುದು ಅಂತ ಗೊತ್ತಾಗಬೇಕಲ್ಲ. ಫಸ್ಟಿಗೆ ಸಿ ಇಟ್ ಈಸ್ ಅನ್ ಆ್ಯಂಡ್ ಗೇಟ್. ಆ್ಯಂಡ್ ಗೇಟಲ್ಲಿ 1 0 ಅಂದರೆ 0 ನಮಗೆ ಗೊತ್ತಿದೆ. ಬಿಕಾಸ್ ಆ್ಯಂಡ್ ಗೇಟ್ ಈಸ್ ದ ಡಿಜಿಟಲ್ ಸರ್ಕ್ಯೂಟ್ ವಿಚ್ ಪ್ರೊಡ್ಯೂಸಸ್ ಹೈ ಔಟ್ಪುಟ್ ವೆನ್ ಬೋತ್ ಇನ್ಪುಟ್ಸ್ ಆರ್ ಹೈ. 1 1 ಇದ್ರೆ ಮಾತ್ರ 1. ಸರಿಯಾ? ಇದು ಯಾವ ಗೇಟು? ಇದು ನಾರ್ ಗೇಟ್. ನಾರ್ ಗೇಟ್ ಅಂದರೆ ನೀವು ಆರ್ ಗೇಟನ ಔಟ್ಪುಟ್ಟನ್ನು ನೆನಪು ಮಾಡ್ಕೊಳ್ಳಿ. ಆರ್ ಗೇಟ್ ಅಂದರೆ 0 0 is 0 ಆರ್ ಗೇಟ್. ಅದೇ ನಾರ್ ಗೇಟಲ್ಲಿ 0 0 ಅಂದರೆ 1. ಇಫ್ ಬೋತ್ ಇನ್ಪುಟ್ಸ್ ಆರ್ ಝೀರೋಸ್, output is 1. That is a NOR gate. But here you see 0 1 is there, output is 0. This is our favorite NAND gate. 0 1 NAND gate ಗೆ AND gate ಅನ್ನು ನೆನಪು ಮಾಡ್ಕೊಳ್ಳಿ. Because AND gate followed by NOT gate is called NAND. AND ಗೆ ನಾಟ್ ಅನ್ನು ಸೇರಿಸಿದರೆ ನ್ಯಾಂಡ್ ಆಗ್ತದೆ. 0 1 ಕೊಟ್ಟಿದ್ದಾರೆ. 0 1 ಆ್ಯಂಡ್ ಗೇಟಿನ ಔಟ್ಪುಟ್ 0, ಕಾಂಪ್ಲಿಮೆಂಟ್ 1 ನೋಡಿ 1. ಸೊ ದಿಸ್ ಈಸ್ ದ ಆನ್ಸರ್. ವಾಟ್ ಅಬೌಟ್ ದ ಲಾಸ್ಟ್? ಇದು ದಿಸ್ ಗೇಟ್ ಈಸ್ ನಾಟ್ ಇನ್ ಅವರ್ ಸಿಲೆಬಸ್, ಬಟ್ ದೇ ವಿಲ್ ಆಸ್ಕ್ ಫಾರ್ ಕಾಂಪಿಟೇಟಿವ್ ಎಕ್ಸಾಮ್. ಇಟ್ ಈಸ್ XNOR ಗೇಟ್. XNOR. What is XNOR gate? What is its output? Its output is Y is equal to A plus circle B complement, or it is XOR gate followed by NOT gate. XOR gate followed by NOT gate. XOR gate means 0 1 1 0 idre output 1. XOR andre XOR when both inputs are different, same alla, when both inputs are different, output is 1. If both inputs are similar, output is 0. That is the property of XOR. Complement of XOR gate is XNOR. ಈ XOR ಗೇಟಿನ ಕಾಂಪ್ಲಿಮೆಂಟ್ XNOR ಅಂದರೆ, ಸೊ 0 1 XNOR ಇದು ಔಟ್ಪುಟ್ ಏನಾಗ್ತದೆ ಅಂದರೆ 0 0. ಸೊ 0 1 ಅಂದರೆ 0ವೇ. Out of this 4 circuits or 4 logic gates, the option C gives output 1. Now we move on to next question. Question number 26. It is a theory based question. The dominant mechanisms for motion of charge carriers in forward and reverse biased silicon PN junction are. ನೋಡಿ, ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ಮತ್ತು ರಿವರ್ಸ್ ಬಯಾಸಲ್ಲಿ ಒಂದು ಸೆಮಿಕಂಡಕ್ಟರ್ ಡಯೋಡ್ ಇರುವಾಗ ಡಾಮಿನೆಂಟ್ ಮೆಕ್ಯಾನಿಸಮ್ ಯಾವುದು ಅಂತ. ವಿ ನೋ ಡ್ಯೂರಿಂಗ್ ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ ದ ಡಾಮಿನೆಂಟ್ ಮೆಕ್ಯಾನಿಸಮ್ ಈಸ್ diffusion of majority carriers across the junction. Diffusion is the process takes place in forward bias. In reverse bias, diode reverse bias alliruvaga width of the depletion layer increases. As width increases, width of the depletion layer increases, drifting of minority carriers increases. So, drift is the process taking place in reverse bias. So, diffusion in forward bias, drift in reverse bias is the right answer for question number 26. Diffusion in forward bias and drift in reverse bias. Now we move on to next question. In forward bias, the diffusion current increases and drift current remains constant. So net current is due to diffusion. In reverse bias, diffusion becomes more difficult. So net current is very small due to drifting of minority carriers. So diffusion is the dominant process in forward bias, resulting the net current. Drifting of minority carriers is the dominant mechanism during reverse bias. For the given combination of gates, if the logic states of the inputs A, B, C are as follows: A, B, C is equal to 0 and A is equal to B is equal to 1, C is equal to 0, then the logic states of the output D are. Just you see the circuit carefully. It is OR gate or it is NAND. ಇದನ್ನು ಫಸ್ಟ್ ನೋಡ್ಕೊಳ್ಳಿ, ಯಾವ ಗೇಟ್ ಕೊಟ್ಟಿದ್ದಾರೆ ಅಂತ. ಸರಿಯಾ? ದೆನ್ ಫಸ್ಟ್ ಕೇಸ್ 3 0 ಅಂತ ಹೇಳಿದ್ದಾರೆ. ಸರಿಯಾ? 3 0. Just if both inputs are 0, OR gate output is 0. ಸರಿಯಾ? Just recall, see the property of OR is 0, 0 is 0 or else the output is high. OR gate ಅಲ್ಲಿ ಎರಡು ಇನ್ಪುಟ್ 0 ಇದ್ರೆ ಮಾತ್ರ ಔಟ್ಪುಟ್ 0 ಇರ್ತದೆ. ಯಾವುದಾದ್ರೂ ಒಂದು ಇನ್ಪುಟ್ ಅಥವಾ ಎರಡು ಇನ್ಪುಟ್ ಹೈ ಆದರೆ ಔಟ್ಪುಟ್ ಈಸ್ ಆಲ್ಸೋ ಹೈ. ಸೊ ಫಾರ್ ಬೋತ್ ಇನ್ಪುಟ್ zeros ಔಟ್ಪುಟ್ ಈಸ್ 0. ದಿಸ್ ಈಸ್ NAND. NAND ಅಂದರೆ ಅಂತ ನಮ್ಮ ತಲೆಯಲ್ಲಿ ಇರಬೇಕು. ಏನು NAND ಅಂದರೆ ಆ್ಯಂಡ್ ಕಾಂಪ್ಲಿಮೆಂಟ್. ಸರಿಯಾ? ಆ್ಯಂಡ್ ಮತ್ತೆ ಕಾಂಪ್ಲಿಮೆಂಟ್ ಇದೆ. ಆ್ಯಂಡ್ ನೋಡಿ 0, 0 ಆ್ಯಂಡ್ 0, 0 ಅಂದರೆ ಎಂಥದ್ದು? ಆ್ಯಂಡ್ ಗೇಟಲ್ಲಿ 0, 0 0ವೇ. ಕಾಂಪ್ಲಿಮೆಂಟ್ ಆಫ್ 0 ಎಂಥದ್ದು? ವಾಟ್ ಈಸ್ ದ ಕಾಂಪ್ಲಿಮೆಂಟ್ ಆಫ್ 0? ಕಾಂಪ್ಲಿಮೆಂಟ್ ಆಫ್ 0 ಈಸ್ 1. ಸೊ when both inputs are 0, all the inputs are zeros, output is 1. This case is solved now. Now we move on to the second case, that is A B1 C0. Now make A1 B1 OR gate, output is 1. Continue with the C0. So 1 0. What is the value of 1 0 for AND gate? First you think of AND, then complement of AND is NAND. So 1 0, AND gate is 0, NAND gate is 1. So in both cases output is 1 1. So in both cases when A B C equal to 0, output is 1. When A is B is 1, C0, output is 1. See the output D, A plus B complement C, because ಇದೆಂಥದ್ದು A plus B C NAND ಆದ್ರಿಂದ A plus B ಡಾಟ್ C ಕಾಂಪ್ಲಿಮೆಂಟ್ ಅದನ್ನೇ ಬರೆದದ್ದು. ಇದು ಹೇಗೆ ಬಂತು? This is by using De Morgan's law. De Morgan's law. जब you see first put A B Z 0 0 ಹಾಕಿ 0 plus 0 0 plus 0 OR gate ಅಲ್ಲಿ ಹೇಳಿದಾನೆ 0 complement 1 1 1 plus 1 is 1 because OR gate. ಅದೇ ರೀತಿ ಎರಡನೇ ಕೇಸ್ becomes see here the question is very easy, direct question. Which gate is represented by this figure? Which gate is represented by this figure? From this figure or logic symbol we can make out the circuit is of NOR gate. It is a direct question. NOR gate symbol is given. Now we move on to next question. See, this question is very important. The diagram of a logic circuit is given below. Just you see the diagram, circuit diagram. We have upper one is OR gate, lower one is OR gate. The output of both OR gates are given to the AND gate. In this case, just you see here the output of the first gate is W plus X because it is OR gate. Now we move on to the lower OR gate. The output is W plus Y. Now these two outputs of the OR gate is given to AND gate. So F output F is equal to output of upper OR gate W plus X, output of the upper OR gate into output of the lower OR gate. Or if we simplify this, W into W plus W into Y plus X into W plus X into Y. Now you see here, we know 1.1 is 1. Similarly, 0.0 is 0. 1.1 is 1, 0.0 is 0. This implies that W.W is 1. W.W, I can write W. So, instead of W.W, I can write single W plus WY plus XW plus XY. Now you see, W plus WY, W is common. I can take that W outside. W into 1 plus Y plus XW plus XY. Clear? Now we move on to, see, 1 plus Y. Y may be 1 or Y may be 0. See, 1 plus 0 is 1. If I take Y as 1, 1 plus 1 is also 1. So, 1 plus Y, I can write it as 1. 1 plus Y is 1. So, W into 1 is W plus XW plus XY. Once again, here we have W common. Take outside W into 1 plus X plus XY. Once again, the same logic, 1 plus Y is 1. Similarly, 1 plus X is also 1. So, W into 1 plus X is 1. W into 1 is W plus X into Y. This is the required answer. That is, W plus X into Y. Option C is the right answer. Now we see the solution. See, output of the upper OR gate, W plus X. Output of the lower OR gate, W plus Y. The output of both OR gates and see the product. Net output F is equal to W plus X dot W plus Y. On simplification, using these properties, we get W plus X into Y. Option C is the right answer. Now we move on to question number 30. Question number 30. See here, in this question we have a photodiode fabricated from a semiconductor with a band gap of 2.5 electron volt. Energy gap is given 2.5 electron volt. It can be detected a signal of wavelength. We want to calculate which signal out of these 4 wavelengths, which signal is detected by the photodiode. First, we convert energy gap, what they given, 2.5 electron volt, convert into joule. After converting energy gap into joules, what you have to do is, this energy gap converted into joule, we know energy gap is equal to h nu or h c by lambda, where c is speed of light. From this it is possible to calculate lambda. Lambda is equal to hc by energy gap in joule, where h is Planck's constant, c is the speed of light, energy gap must be in joules. If you simplify this, we get lambda as 500 nanometer. If you use this h value, standard value of Planck's constant, then speed of light, energy gap already be converted into joule. If you simplify this, we get lambda as 500 nanometer. Just you see, out of these 4 values, the value of wavelength which is less than lambda, lambda dash less than lambda will be detected. Lambda dash less than lambda will be detected because lambda dash is called lambda is called threshold wavelength. The signal having wavelength less than the threshold wavelength are detected. So the correct option for this question is option B. See here, only signals having wavelength less than the threshold wavelength will be detected. We calculated the threshold wavelength by using the formula lambda is equal to hc by E. H is Planck's constant, c is speed of light, E is energy gap, convert into joules. On simplification, we get threshold wavelength as 500 nanometer. Threshold wavelength is 500 nanometer. Wavelength of the signal, if it is less than 500 nanometer, will be detected by the photodiode. So the option B is the right answer. Now we move on to question number 31. Question number 31. A light emitting diode has a voltage drop of 2 volt. Voltage drop across light emitting diode is 2 volt. And it passes a current of 10 milliampere. Current flowing through the diode is 10 milliampere. The diode is connected to 6 volt battery through a limiting resistor. What is limiting resistor? A resistor which controls the current in the circuit. So it is called a limiting resistor. See here, this is the limiting resistor. This is the light emitting diode connected to 6 volt. Here the voltage drop is given 2 volt, current through the diode is given, current through the diode is 10 milliampere. Say, let R be the resistance of the current limiting resistor. This resistor na value R anta takolva. By using Ohm's law, total voltage EMF E is equal to current 10 milliampere into resistance plus 2 volt. What is 2 volt here? 2 volt is the voltage drop across light emitting diode, or 6 minus 2, 4 is equal to 10 milliampere into R, or 4 by 10 milliampere is nothing but R. 4 by 10 is 0.4 milliampere is 0.4 kilo ohm is R, because reciprocal of milli is kilo. So 0.4 kilo ohm is nothing but 400 ohm is the value of resistance. Option A is the right answer. Just we move on to the solution. See, voltage across the resistor, R is 6 volt minus volt, which is nothing but 4 volt. Current in the circuit I is 10 milliampere. We know V is equal to I into R, R is equal to V by I. If I simplify, we get 400 ohm. So option A is the right answer for question number 31. Now we move on to question number 32. The correct symbol of Zener diode. It is a direct question. If you know the symbols of the diodes, logic gates, etc., we get one question. See, the correct symbol of Zener diode, it is a basic question. This is the correct symbol of Zener diode, that is nothing but option A is the right answer. Now we move on to question number 33. This question is also based on the symbols only. The logic gate symbol for OR, NOR and NAND respectively. OR, NOR and NAND. See here, by seeing this we can make out it is an OR gate. This is AND gate. This is NOR gate. The last gate is nothing but a NAND. By seeing this, we can make out what they want is only OR, NOR and NAND 1, 3 and 4 in the order. So option C is the right answer. First gate is OR gate, second gate is AND gate, third gate is NOR gate, fourth gate is NAND gate. They want only the three gates OR, NOR and NAND. Option C, first, third and fourth are the correct answer. Option C. Now we move on to question number 34. See, it is also theory based question. First, the approximate ratio of resistances in the forward and reverse bias of the PN junction. We know when diode is in forward bias, diode forward bias alli work ಮಾಡ್ತಾ ಇದ್ರೆ it acts as closed switch, or current through the diode, resistance of the diode in forward bias is few 10 ohms. We take it as 10 ohm. Current through the diode is 10 ohm. Now, in the reverse bias, when the diode is operated in reverse bias, the diode acts as open switch, resistance is high, reverse bias of the reverse resistance of the diode is about 10 power 5 ohm. They want the ratio forward resistance is to reverse resistance, that is 10 is to 10 power 5, which is nothing but 1 is to 10 power 4. Option B is the right answer. 1 is to 10 power 4 is the ratio of forward and reverse resistance of the diode. That is, when the diode is operated in forward bias, resistance will be low. When the diode is operated in the reverse bias, resistance will be high. So, the ratio of the resistance in forward and reverse bias is about 1 is to 10 power 4. See, resistance in forward biasing nearly 10 ohm, it is taken. Reverse biasing 10 power 5 ohm. Ratio 1 by 10 power 4. 1 is to 10 power 4. Now we move on to question number 35, the last question. See, to get an output 1 from the circuit shown in the figure, the input must be. Just you see the circuit carefully. It is an OR gate. It is an AND gate. Clear? ನೋಡ್ಕೊಳ್ಳಿ, ಒಂದನೇದು OR gate, ಎರಡನೇದು AND gate. OR gate we know they want here output of the circuit is 1. See, they want the output 1. We know AND gate gives one high output only when both inputs are 1. So, input of AND gate be 1 and 1, right? So option C must be 1. The input C must be 1. Input C1, we have only one option. See, C1. So option C is the right answer. This method is called shortcut method. Here we started from output side, we move on to the input side. See, output is 1 and output is 1 when both inputs are 1. As C is 1, only one option they given C1, so that is the right answer. The actual way of doing this is just by constructing the Boolean expression and writing the table. See, the Boolean expression for the output Y is A plus B, which is the OR gate output, and AND gate full output Y is equal to A plus B dot C. Draw the truth table. We can make out when C is 1, C1, A1, B0. C1, A1, B0. Here, in this case, we get output is 1. So, output by preparing the truth table, it is possible to say output is 1 when C is 1, A is 1, B is 0. Instead of preparing the truth table, if you analyze the circuit from output side, it is possible to get the option early. This is about question number 35. So, in this chapter, from this chapter Semiconductor Electronics, hardly we get 2 or 3 questions. 2 or 3 questions for KSET or NEET. Almost all questions are direct. Just one question will be from the logic gate side, the other questions will be from PN junction or basics of energy band diagram, semiconductor diode or rectifier circuits. So with this, we discussed nearly 35 questions in this chapter. In addition to this, you should work out similar questions from different competitive examination books. Thank you, one and all.